Hello, good evening to all of you. Today we want to learn the BTech Mathematics 2 paper code is M201. Under this, we are going to learn the module 4, that is the Laplace Transformation, lecture 31. Laplace Transformation, lecture 31, paper code M201, module 4. First, we are going to discuss about the preface and introduction to the Laplace transformation, definitions and the existence of the Laplace transformation. Laplace transformation in the short form we can write in the LT of the elementary function. Laplace transformation of elementary functions. Introduction to the Laplace transformation. Preface and introduction to the Laplace transformation. One of the most important tasks is the analysis and design of the physical system, and its control is the mathematical modeling of the system. Since every motion can be described mathematically by some differential equation. That differential equation we can say the ordinary or the partial differential equation. The mathematical model of a system involves invariably differential equation whose solutions provide the output of the system. The operations of differentiating function is a transformation from function ft to a function f dash t. When we are differentiating a function ft, we are denoting the differentiations of the function by f dash t. If the operation is represented by the symbol capital D, the transformation can be written as d of ft. This should be the ft equal to f dash t. This is ft equal to f dash t. The function f dash t is the image of the function ft under the transformation. The function 2t, for example, is the image of the function t squared. If we take the differentiation of the t squared, we will get the 2t. So 2t is the image of the function t squared under the differentiation. Another transformation of function is that of the integration. I of ft equal to 0 to x ft dt. The result of this operation is a function capital Fx. The image of small ft under this transformation. In each of the above examples are inverse transformations exist, provided some sufficient conditions are being satisfied by ft. The transformation t, ft, t is denoting the transformations of the function ft, is said to be linear if for every pair of functions f1t and f2t. Let us consider the two functions, one is f1t, another is f2t. For each pair of constant c1 we are considering for the F1t and C2 for the F2t. It satisfies the relation transformation T of C1 F1t plus C2 F2t equal to C1 C1 transformation T of F1t plus C2 transformation of F2t. Thus, in a linear transformation, the transform of a linear combinations of the two functions is the same linear combination of the transformations of those functions. Linear integral transformation of the function of t defined on a finite or a infinite interval a less than t, t less than b are sometimes very useful in solving the problems in differential equation. Let KTS denotes the sum prescribed function of a variable t and a parameter s. Let KTS denote some prescribed function of a variable t. The parameter is a general linear integral transformation of a function ft with respect to KTS called the called the kernel is represented by the expression. We are considering the transformation that is the t ft small ft equal to integration from a to b ft kts dt. This is the linear integral transformation represented by this expression. It represents a function capital Fs. From the right hand side, we will get a function of capital Fs, but it is the limit a to b that t will be converted to the expression of a to b and s is there. So we will get a function of capital Fs. That means we will get another function in terms of the s, known as the image or the transformation of the function small ft. It is seen that with certain kernel KTS of the transformation when applied to a prescribed linear differential equation in ft, it changes its form into a algebraic expression that is capital Fs. That involves certain boundary values of the function small ft. Consequently, many problems in ordinary differential equations transform into algebraic problems. Taking the image of the unknown functions, if an inverse transformation is possible, the solution of the original problem can be determined. That means we are taking the transformation on small ft, we will get the capital Fs. If there exists another inverse transformation from that capital Fs, we will get the original one solution. That is, the solution of the original problem can be determined. Boundary value problems in partial differential equation can be simplified in a similar way. Boundary value problem we will get in the wave equation, also we will get in the heat equation. Now move to the actual Laplace transformation. What is the Laplace transformation? The Laplace transformation is an integral transform. It is effective for the solution of many problems arising in science and engineering. Laplace transformation converts an ordinary differential equation with some given initial conditions into an algebraic equation. Applying the Laplace transformation, we convert the differential equation to an algebraic equation. Finally, using the inverse Laplace transformation, we recover the original function. So considering its usefulness, we shall first consider Laplace transformation with its properties and then discuss the methods of solution of differential equation by the application of this transformation. Question: the kernel of integral transformation is, option is there A, B, C, D. A is KT, B is KS, C is KTS, D is none of this. What would be the answer of this? I am providing the time for this. Again, I am repeating that the question. The kernel of integral transformation is A, KT, option B, KS, option C, KTS, D, none of this. What we learn in the integral transformation, integration over A to B, Ft multiplied by the kernel, that is KTS dt. Therefore, KTS is the kernel of the integral transformation. That is, answer C is correct. Laplace transformation. Now we move to the actual definition of the Laplace transformation. Previous slide and the previous one slide we already learned, that is the application of the transformation, Laplace transformation, where we can apply the Laplace transformation. Mainly we are using the Laplace transformation to solve the differential equation. First, we convert the differential equation to an algebraic equation by using the Laplace transformation. After that, some simplification, again we convert that algebraic equation by using the inverse Laplace transformation to the original one. From that, we can find out the solution of the differential equation. Now, the definition of the Laplace transformation. A real valued function small ft of real variable t always greater than equal to 0. T is start from 0 and it is always greater than 0. That satisfies the conditions. Integration over 0 to infinity modulus of ft e to the power minus sigma t dt, that is value is less than infinity. That means the existence of this integration is value is the convergence that is less than infinity, where less than infinity means we will get the finite value of this integration, and sigma is real. The Laplace transformation of ft, that the function small ft, denoted by the symbol L. L normally we are using here and throughout this chapter and throughout our discussion. L represent the Laplace transformation, and function we can write within the bracket or in the curly bracket, third bracket or within the curly bracket, braces, third braces, or we can use the curly braces. is defined as Fs. Fs equal to Laplace transformation of Ft of the function real valued function Ft. Laplace transformation of Ft equal to 0 to infinity Ft e to the power minus st dt. So in this case, Ft kst. So in this case, kts is our the e to the power minus st. Kts, or you can say also the kst. That is our e to the power minus st. So you can say e to the power minus st is the kernel of the Laplace transformation. This is our the definition of the Laplace transformation. And after this integration, what we will get? We will get another function, that is function of the s. That's why we are writing it is a capital S. So from that we can write here in the right hand side capital S. We can write it capital Fs is equal to L Laplace transformation of Ft equal to 0 to infinity Ft e to the power minus st dt. This is, we can write the one, that expression or the definition. Fs is 1. The variable s is referred to as the Laplace operator or the transformation parameter. And in this case, that is the kernel of the transformation kts equal to e to the power minus st is known as the kernel of the transformation. Now, remarks. Laplace transformation is a kind of the integral transformation. The Laplace operator S is the Laplace operator, the small s, Laplace operator or the transformation parameter. That S may be complex number. However, in this throughout this chapter, we are considering S is real. We consider S to be real number unless otherwise specified in this chapter. So throughout this Laplace transformation chapter in your syllabus, we are considering S is the real. The integral on the right hand side is an improper integral. Why it is improper integral? Lower limit is the 0 and upper limit is the infinity. That's why it is an improper integral. 0 to infinity ft e to the power minus st dt. That's why we say it is an improper integral. It is evaluated as limit. We know how to find out the improper integral. In this case, upper limit is the infinity. So we can replace the infinity by b and take the limit b tends to infinity ft to the power minus st, provided the limit exists. After finding the integration of this and b tends to infinity, their limit is exists, then we say the improper integral is exist. Therefore, that is, we say that the Laplace transformation is exist. Question is that the kernel of Laplace transformation is e to the power minus s, e to the power minus t, e to the power st, e to the power minus st. What is the kernel of Laplace transformation? previous slide, as we already learned, what is the kernel of the Laplace transformation? We learned that KTS is equal to kernel of the Laplace transformation is e to the power minus st. That means option D is the correct answer. Now we can proceed to the next. Laplace transformation of some elementary functions. 1. Laplace transformation of ft is equal to 1 when ft is 1 and t greater than equal to 0. As per definition L1, Laplace transformation of ft equal to, we can write here Laplace transformation of ft equal to Laplace transformation of 1 equal to 0 to infinity 1 e to the power minus st dt. So by definition, since it is an improper integral, we have to change infinity by b. This is the upper limit, and b tends to infinity. 1, that is the coefficient of e to the power minus st. So e to the power minus st dt. Now we know the integration of e to the power minus st dt. E to the power minus st dt is e to the power minus st, and since there is the minus st is there, so e to the power minus st divided by minus s, and limit is 0 to b and outside, that is limit b tends to infinity. So whatever the result we will get from that, we have to find out the limit b tends to infinity. E to the power minus st, 1 by s, no, 1 missing is there. 1 by s will be here, 1 by s is here, and e to the power minus sb minus 1. So when b tends to infinity, e to the power minus sb now limit b tends to infinity, e to the power minus st by minus s 0 to b equal to limit b tends to infinity. We can take common out 1 by minus s minus 1 by s, and from that e to the power minus sb minus 1. When s is 0, e to the power 0, that is minus 1. And from the limit we will get, this will be 0. So minus and minus 1, minus 1 by s and minus 1, we will get 1 by s. Therefore, we can write Laplace transformation of 1 equal to 1 by s and s greater than 0. So this is the first result we show here, Laplace transformation of 1. That means when the function ft is equal to 1, then our result is Laplace transformation of 1 is equal to 1 by s and s greater than 0. Each and every result we have to remember. Now, Laplace transformation of ft is equal to t to the power n, where t is greater than equal to 0. Here, our function ft is t to the power n. So, as per definition of the Laplace transformation of t to the power n, we can write here also another extra in the left hand side, Laplace transformation of ft. And next is Laplace transformation of t to the power n is equal to 0 to infinity t to the power e to the power minus xt dt. This is an improper integration. So take in place of the infinity, we can take the b and limit b tends to infinity. So our integration is 0 to b t to the power n e to the power minus st dt, t greater than equal to 0. Now we can replace or we can substitute st equal to u equal to st. Therefore, we will get du equal to s dt. So from that we will get t to the power n differentiating this du equal to s dt. So from that we will get the one s, and from here we will get the another s. So dt equal to dt, from that we will get dt equal to u du by s. So from that we will get u to the power n e to the power minus u du, and our limit is b tends to infinity, and the integration limit will be changed when t is 0, u is 0. When t is b, u equal to sb. So 0 to limit is sb, u to the power n, u to the power minus u du. This is we can write in the form of e to the power minus u, e to the power n plus 1 minus 1. So this is 0 to infinity in the form of the gamma function. Now we can omit the b and we can take the original form 0 to infinity e to the power minus u to the power n plus 1. U to the power n, we can write it u to the power n plus 1 minus 1. So this is the form of the gamma function. If we recall the memory from the first semester chapter, the improper integration. 1 by s to the power n plus 1. 1s will get from this, and another s to the power n will get from this t to the power n. T to the power n means u by s to the power n. From that 1 s to the power n and 1 is from our dt. So s to the power n plus 1. Gamma function, this is gamma n plus 1. So this is we can write in the form gamma n plus 1 by s to the power n plus 1, where s is greater than 0. So therefore our result, Laplace transformation of t to the power n equal to gamma n plus 1 by s to the power n plus 1. S is greater than 0, n is greater than minus 1. N is greater than minus 1. Here, if n is the positive integer, then we can write gamma n plus 1 equal to n gamma n. Basically, gamma n plus 1 equal to n gamma n equal to n factorial. So when n is a positive integer, so we can write Laplace transformation of t to the power n equal to n factorial by s to the power n plus 1. S is greater than 0 and n is positive integer. Laplace transformation of ft equal to e to the power at, t greater than equal to 0. As usual, we know the definition of the Laplace transformation. Laplace transformation of e to the power at. E to the power at is our ft. So 0 to infinity e to the power at into e to the power minus st dt. For improper integration, b tends to infinity, 0 to b, e to the power at and e to the power minus st. So adding the two indices, we'll get e to the power minus, we can take the minus before, so s minus a t dt, t greater than equal to 0. So we know the integration of e to the power minus st, we can treat s minus a as a one quantity. So 1 by s minus a, and limit, we can change that minus is there and we are changing this minus here, 1 minus. So 1 minus from here and another 1 minus, that is cancel out. So limit b tends to infinity, 1 minus e to the power minus s minus a b. When b tends to infinity, this is equal to 0. So from that we will get 1 into 1 minus 1 by s minus a. So we get 1 by s minus a. S is greater than a. So Laplace transformation of e to the power a t equal to 1 by s minus a. When it is positive, e to the power at, that means e to the power at, e to the power is the positive, then it is s minus a. Same way we can find out e to the power minus 80. When it is minus, this will be plus and s greater than a. Most important transformation of the trigonometric transformation, when our ft is sin 80 and ft equal to cos 80 and t is greater than equal to 0. At the same time, we want to find out the Laplace transformation of the two trigonometric functions. One is sin 80, Laplace transformation of sin 80, and Laplace transformation of cos 80. As per definition, as per our definition of the Laplace transformation of sin 80 equal to 0 to infinity sin 80 e to the power minus st dt, t greater than equal to 0, and Laplace transformation of cos 80 equal to 0 to infinity cos 80 e to the power minus st dt, t greater than equal to 0. We know e to the power minus 80 equal to cos 80 plus I sin 80. This is the known result. With the help of this, we want to find out the Laplace transformation of sin 80 and Laplace transformation of cos 80 by equating the real and imaginary part. We can take the Laplace transformation of both the sides. So Laplace transformation of e to the power I at equal to Laplace transformation of cos 80 plus I sin 80. From that, we can write Laplace transformation of cos 80 plus I Laplace transformation of 80 using the linearity property of the Laplace transformation. That we learn also next, properties of the Laplace transformation. And also, we learn that the transformation is the linear, follows the linearity property. Transformation of C1 F1 plus C2 F2 equal to C1 transformation of F1 plus C2 into transformation of F2, that we already learned. So transformation, integral transformation follows the linearity property. From that, we are using the linearity property of the Laplace transformation that we learn in the next, all the properties of the Laplace transformation. So from that, from the left hand side, we know Laplace transformation e to the power I at equal to 1 by s minus I. Just to learn Laplace transformation of e to the power at, that is 1 by s minus a. So here, instead of a, there is ia. So a will be replaced by ia. So 1 by s minus ia by the property 3. Just we learn that. From that, we can write multiplying the numerator and denominator by s plus ia. Multiplying the numerator and denominator by s plus ia, as s plus ia not equal to 0. So multiplying this, what we will get? In the denominator s square plus s square and numerator is s plus ia. This is we can write in the two part. One is the real part, another is the imaginary part. From that, s by s square plus s square plus I into a by s square plus s square. There is the two part is there, real and imaginary. Now from the one, Laplace transformation of cos at plus I Laplace transformation of sin at equal to Laplace transformation of e to the power I at equal to this part s by s square plus s square plus I into a by s square plus s square. Now equating the real and imaginary part, we will get real part is s by s square plus s square. Here our real part is cos at. From that we can say Laplace transformation of cos at equal to s by s square plus s square is greater than 0. And from the equating the imaginary part, we will get Laplace transformation of sin at equal to a by s square plus s square and s greater than 0. So this is the two important result for the trigonometric function, Laplace transformation of the trigonometric function sin at and cos at. You have to remember this result. Next lecture class is lecture 32. Paper code in M201 module is 4 Laplace transformation. We will continue that the Laplace transformation of elementary functions, existence theorem of the Laplace transformation, existence theorem of Laplace transformation, properties of the Laplace transformation. Then I want to stop right now for this class.